Okay, so now we're going to compute volume change. We've already computed cross-sectional area change using the little trapezoids and triangles. And so for volume change, what we have is a cross-section and we have another cross-section, and this is bounding a control volume. And we have the length in between measured along the river. So if you take the average of the cross-sectional area changes on those two bounding cross-sections, multiplied by the linear distance in between, river-wise distance, then you have a volume. And so volume from 1 to 2 in this case is the average here of cross-sectional area at 1 and area at 2. So divided by 2 to get the average, times by that length in between. And the volume from 1 all the way to 3 is the volume from 1 to 2 plus the volume from 2 to 3. All right, so now we're going to talk about how to compute a longitudinal cumulative volume change curve. And the way this works is we are going to start upstream and we are going to accumulate the volume change as we move downstream. So right at river station 1000, there is zero volume change because there's no volume. It's just a location. But by the time we get to river station 800, we'll have the volume change that's between 800 and 1000, which will compute, as we just explained, how to compute volume change between two bounding cross sections. So we compute the volume change in this segment 1, and we plot it on our graph as being at river station 800, because that's all the volume change that's occurred by the time you start at the upstream and get to 800. Then we compute the volume change in segment 2, and but what we plot at river station here 500 is the volume change in segment 1 plus the volume change in segment 2, because we are accumulating the volume change from upstream to downstream as we move downstream. Then we get the volume change in segment 3, and we plot the volume that is segment 1 plus segment 2 plus segment 3. We plot that at river station 300, and so on and so forth. So what we end up with is, it could be something like this, depending on your volume change. Well, in this case, so we're starting at the upstream end, and it's at 0 at the upstream end, and then we've got a volume change, and we plot it. Then we've got volume change in both segments, and we plot it here. The volume change in all 3 segments added together, we plot it there. The volume change in all 4 segments added together, we plot it here. And when you have a change, longitudinal cumulative volume change curve that looks like this tells you some important things. This tells you, first of all, overall, this reach of the river is aggradational. It's depositing. The volume change is positive. Basically positive everywhere. The whole thing has been a grading, except this very last segment where it stays flat. That means that segment didn't change. So we can see that it graded the most from river mile 500 to 300, and it remained stable from about 100 to 0. So here is an actual longitudinal cumulative volume change curve. This is on the Missouri River, created using cross-section viewer software, which we'll discuss later. And you can see regions where the bed has been degrading. So now here still starting at the upstream end at the higher numbers upstream, and that starts at 0, but the bed is going down in general. And there's some areas where it's going, the rate of degradation is less. There's some areas where the rate of degradation is very high, and then there's some areas where the bed went up between the 2 years that we are looking at. So you could think about this as, well, a lot of this degraded, and some of the sediment that washed downstream ended up aggrading or depositing in this location. So overall, you can see areas on this 500 miles of degradation, of aggradation, a little bit, maybe stability right around here. And so this is a very useful information dense curve. Okay, second example is how would you compute a channel depth distribution? So in the example of the pallid sturgeon and eating habitat depths for the depths for different well, defining the depths for the habitat purposes, defining what the habitat is for a shallow water habitat. This plot here is showing more of a spatially distributed approach, so a GIS approach. And if you have really dense data, you could do this if you had multi-beam sonar or just a really dense survey. But if your data is cross sections, like it is on the Missouri River, then it's harder to produce something like this. Also, surface generation is tricky. It's time consuming. There's a lot of issues that can happen, like having a point up on the bank being interpolated down to points in the bed and giving yourself funny edge effects on the channel. And a lot of other things that can be time consuming. And if your data is collected as cross sections, building a surface is totally unnecessary. You can just analyze them at the cross sections. And the way that that is done is there's a you basically break your channel into vertical increments. And so for here, the depth from 0 to 5 feet. So there's a depth increment, and there is a certain width of the channel that if you start at that 5-foot level and you go up to the 0, you could get the area of this little triangle and the area of that little triangle. But what we're going to do is we're going to do it based on the width. So we've got this width C that corresponds to this increment of depth. And then we've got the width D. So for 0 to 5, we would add up the width C and the width D. For the depth increment from 0 down to 10, then we've got a bigger triangle here and a bigger triangle over there. And so we can find that width as well, and we could add that up. And then if we wanted from 5 to 10, we would just subtract the previous widths that we computed from 0 to 5 from the larger 0 to 10. And then so on and so forth. If we want to get the depths that fall between 0 and 15, the depths that fall between 0 and 20 will be this width here. It'll be a width here in the middle, and it'll be a width here on the side. So basically, anytime the cross-section intersects with the line that represents the depth we're looking at, then we're going to have to find the width of that little bounding area. And 0 to 25 feet in this case is the entire cross-section. And so then, as I said, if we want to get just the individual increments, we can subtract the other increments in order to get the depth distribution. Okay, so the way we do this when we've got now cross sections and we have some distance between them is we average. So if we have the width of the depths from 0 to 5, let's say there's 25 feet of width, and we've got 30 feet of width in this second cross section here from that 0 to 5 foot depth, then we would average those two. So the 20, oh, I got a typo here. Oh no, I'm looking here from 0 to 5. Okay, so at cross section 1, the depth is 20 feet. Cross section 2, the width of that depth is 30 feet. So to go from the surface area from 0 to 5 feet, we've got 1,000 feet, this length in between. That's times by the average of those two widths, so 20 plus 30 divided by 2, and that would give us the surface area between these two cross sections corresponding to 0 to 5 feet of depth. And then we're adding the second one here, so then it's 800 feet is the length times the average width for that depth increment, in this case 30 feet plus 25 feet divided by 2. So this altogether is giving us then a certain number of square feet converted to acres, and that's telling us how much surface area exists in that depth increment all the way from cross section 1 to cross section 3. Okay, so the Missouri River, here's an example, and you can see the data for this cross section right here, which we've got in these two different years. And as I showed you before, the cross section data on the Missouri is very, very dense. And this shows the area with depths less than, and so the acreage that falls into each of these increments. So the total acreage for the reach that I was looking at that falls into these different depth increments. Now, if I wanted to do that for the entire 500 miles, and I have 10,548 cross sections, and do it for all of those, you can get the idea that if you did this by hand at every single cross section, when you have this many cross sections, it would be very time consuming. So we've developed software to let you do this quickly. So the total time, start to finish, to do it with the software was 1.5 minutes. So once you have all your cross-section data into the software in the right format, you can just say, give me a depth distribution. This is the increment I want. Click go, and 1.5 minutes, and it's created a distribution showing the acreage of all the different depths. And this software is the cross-section viewer software. It was developed by myself while I was at the Corps of Engineers, kind of planning out the functionality and how I wanted it to work. And then Dr. Philip Bailey from North Arrow Research, who runs his own software development company, but he has his PhD in GIS and remote sensing. So he writes software specifically for geospatial analyses. Anyway, so we partnered, and Philip then wrote this software over the course of several years and multiple contracts with him. He's added a lot of the functionality that I would want when I'm analyzing cross sections, and so it's very, very useful software. The basic framework, it's no longer an Access database, it's a SQL database, but there's a database that has the underlying data. It's got the XYZ points and stations, elevations, the distance of where the cross sections are from each other, things like that. And then you can add lots of other things like water surfaces and stations of interest. And then there's a nimble little tool that accesses the database and does math on it to compute your geomorphic information. And I say nimble because the Corps of Engineers computers were really, really tied down to where the users aren't allowed to install new software. And so making this tool very nimble to where it doesn't actually have to be installed was important. So even if you don't have admin rights on your computer, you can still use this software just fine. You can also install it, and then there's some advantages of doing it that way. But if you don't have admin rights or don't want to install it, there's a version that you can just copy over and use without any installation or admin rights. Okay, I'm going to run through some examples using the cross-section viewer, and then what you'll be doing for your homework are computing some of these various things. You'll do some work by hand, and then you'll also do some using the cross-section viewer. So I am now going to switch and kind of show you some of what the cross-section viewer can do.